Okay, I wanted to give you guys a quick update of what's going on here. This facility is the test beam facility at CERN. So at CERN, there's a thing called the Large Hadron Collider. It is a 17-mile ring that's 300 feet underground. And it starts with a bottle of hydrogen, which is a proton and an electron. And they put it in a very strong electric field, which pulls the positive charge one direction, which is my favorite band, and the electron, which is negatively charged, in the opposite direction. So it rips the electrons out of the atom, so you have pure protons. And then it takes a magnetic field, since the proton is charged, it makes it drive a negative pulse, a wave. It pulses a magnet, and it starts to accelerate the proton down a pipe. And then it puts it into a circular accelerator where they slowly increase the frequency of the magnet, and then they take that beam, and there's two options. They could send it into the LHC, or they could send it here. And when they send it here, it comes into this building further that way. It hits a bunch of targets, so the protons can turn into, when it smashes into, say, a graphite target or something, it can turn into protons. Well, that's what it starts as. Protons can turn into electrons, positrons, pions, muons, whatever, lots of different particles. So CERN is a particle physics research facility, and they want to study particles. So you need to make particle detectors to study particles. This place is where you characterize particle detectors, because we can generate a clean beam of pure particles of a specific energy. So you want to study how your electrons do in your particle detector. You want to study how pions do, how kaons do. You come here, you install your detector, and you make that measurement. And then when you put it in a real experiment where you don't get to control what particles come out, then you can have a pretty good idea of what particles came out. So along these lines, there's 4 beam lines. 1, 2, 3, 4 beam lines. You can see that's my experiment there. And then this is another beam line. And these beam lines, they go all the way down the facility. And see these yellow boxes? They have numbers on the top. 451, 447, 445. These are all control rooms for the various stations where you can set experiments up along the beam line. And then we all take turns on a single beam line. We all take turns deciding what we all take turns who gets to use the beam or not. Because if your stuff is in the beam, then you can see the table is moving. That's a daisy table alarm. It means they're moving their they're trying to align there. Anyway, so all these people, we can all use these beam lines to get the measurements we want. So our experiment is down there under that black cloth right there. So when the beam comes in, all of particle physics is basically a timing problem. So the particles come in, they're in little bunches, and they go boom, 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 boom into our detector. Well, how do you know they come in? We have a detector which just responds to particles but doesn't disturb them. So the particles go through and make a signal, bloop. Then we take that signal, we put it into something called a discriminator. The discriminator, we set a threshold. As long as the pulse is big enough, it takes that signal and it turns it into a bigger pulse, which we can use to trigger the rest of our data acquisition. So these particles come flying into our thing, and then we have data acquisition cards, 32 channels, and they are constantly listening, and they wait for that trigger. And they take that trigger, so they're constantly saving data in the memory buffer, and then when the trigger happens, you can tell it to save, so many samples before and so many samples after the trigger, so that you can actually see, boom, your pulse when it came through. So we had to set up the trigger. There's a complication where our data acquisition device there's 2 of them. We had to synchronize them. And in order to synchronize them, we had to make sure that when one was busy, it wouldn't take an event, the other one wouldn't take an event. So we have it set to there's a busy signal, basically. I'm busy, so it doesn't allow any triggers in while it's busy. So setting up the trigger was tricky. And our module down there, all it does is measure electrons. And we're trying to show that we can measure the timing of when an electron hits our detector to within a few picoseconds. Okay, so that's the experiment. That's where all the stuff is. Let's go in the control room now and take a look at what we got going on in here. So this is the control room, and so we just finished a run So here's where we can control the magnets and the energies and everything. These are all the magnets that are used to get the beam to us and the beam that we want. So I'm going to change to a 50 GeV electron beam. So I'm going to load this beam file. There we go. And now what you're going to see is all of these magnets going out of, well, they were here, and now we have a new setting, and now they all have to move to the new setting. Okay, so now our beam is all green. I'll go over here to the data acquisition system. I'll start recording data. Okay, our thing is opened up. We're gonna start taking events now. Over here we can see every time a beam, this diagonal line means the beam is dumping. So this is shooting particles down right now, and now it's gonna refill. This is our controller to move the daisy table up and down, move our thing around, get it lined up. This is our high voltage connections from our high voltage system here. The high voltage system goes down, the cables go down into the enclosure because we want to change these up here depending on our data. And then we have the scaler here, which counts how many events we get in a spill. So let's wait. Beam is coming now, and you can see we're getting 8,000 events per spill. So we record about 8,000 events per spill. And then we come over here. We take data in chunks of 30,000 events. So once we hit 30,000 events, which we just did, then this pops up with all 32 channels so that we can immediately see that our 8 channels here have signals and our 8 channels here have signals. And as long as we have signals, then we are good to go. So it's been a challenge to get this going. This is the first time I've had to do this pretty much by myself. There's another guy here, Berkan from Turkey, and he's very good at setting up trigger stuff. And so I had to assemble the module, I had to put it together, I had to debug it, I had to get the code working. I wrote this thing so that we could have real time, well, I didn't write it, but, well, I sort of wrote it. I made it so it does this. So automatically when a reading is done, when we get through 30,000 events, we can immediately glance at it. So I made it so it automatically updates, and it'll do that here in a second. Boom, there it is. And then we can look at it. So we also have wire chamber data here. So this is the X and Y of a grid of wires down there. And when a particle travels through the wires are charged, and it's gonna feel a tug from the charged particle that passes through it. And that tug is gonna show up as a little pulse of energy down the wires. So when the signal happens, tells you, rate times time is distance, tells you where in X and where in Y. The time difference between these two tells you where and where the particle is in the wire chamber. So that's pretty cool. And that's the reason that I've been so distracted, because it's 2 of us here doing all of this, and it's been challenging, but now we're taking real good data, and we're gonna have what we need here very shortly. So we can't ask for better than that. See you guys.